Swayam Prabha. Digital India. Educated India.
All right. So, good morning, good afternoon, and welcome back. This is our course on analysis and design of rigid pavements. And we have, in the previous four lectures, we went through module one. So, module one was meant to be more of an introductory module. We talked about the need and the importance of rigid pavements. We particularly talked about different types of rigid pavements. That's JPCP, CRCP, JRCP, and PCP, of which I mentioned that primarily we'll be interested in JPCP for the most part of this course. A little bit of CRCP also will do. JRCP is rarely used, and PCP is a very specialized application as of now. So largely we'll be focusing on JPCP and a little bit of CRCP. Now, regardless of what type of rigid pavement we have, we saw that all rigid pavements consist of a certain number of layers. That was the surface layer, we had the base layer, optionally we had a sub-base layer, and the base and the sub-base are basically giving a platform for construction. Most of the load is being borne by the slab itself. And finally, the last layer is the subgrade, which is the natural soil. We looked at the different materials that these are made of. In particular, we looked at the different properties of the materials. And I had mentioned in that lecture that we aren't just interested in characterizing the materials using any property. First of all, when we say we want to characterize a material, basically we want to understand if we apply a load on it, what type of stresses, strains, and deflections develop in it, for which we need some sort of a mathematical theory. And today's lecture will be looking at the main mathematical theory for rigid pavements. So we need some sort of a mathematical theory. And on the other side, we need a test which can actually measure that property, which is reasonable and convenient. So in particular, we saw that for a rigid pavement, the slab is modeled using two properties, which are the elastic properties, namely the elastic modulus and the Poisson's ratio. That's one. And then we saw that the subgrade is characterized using what is called the modulus of subgrade reaction. In short, it's sometimes also just called the K value. So what we saw was that we had various ways of measuring these properties directly, but in general, those techniques are not particularly convenient. So we saw there are simpler techniques and a variety of correlations that we use to relate these properties. Finally, we looked at certain distresses which develop in rigid pavements as well. So that was module one. Now we're going to be starting a series of lectures, about 9 to 10 lectures in module 2. And module 2 is on analysis of rigid pavements. So just to define what do I mean by analysis of rigid pavements, I basically mean that if I have a rigid pavement, typically that means JPCP. If I have a JPCP with some configuration, some properties, some thickness, and I apply a certain load on it at a certain location, I want to know what are the critical stresses, and I'll define critical stresses today. I want to know what are the critical stresses that are developed in the pavement. That's basically what we mean by analysis of rigid pavements. So in module 2, we are largely going to be focusing on classical methods for analysis of rigid pavements. Now, what do we mean by classical methods? One way to look at it is they are old methods. They are methods which were developed, as we shall see, the particular method we're going to talk about in today's lecture and subsequent lectures is developed over 100 years ago. Now, the one important thing to understand about classical methods is there were no computers back then, or at least no electronic computers as we know them today. So, because there were no computers, one of the defining characteristics of classical methods is that we have to do basically hand calculations. Of course, today we can also calculate it on Excel, we could write a code to do it, but in general, there is a nice closed form solution that will give us the answer. In developing those closed form solutions, it's very hard, firstly, to develop them, but fortunately, somebody's already done it for us. But in developing those solutions, a series of assumptions are made along the way. And therefore, the solutions are to be understood to have some amount of approximation built into them. And we shall see in subsequent lectures what some of these approximations are, what some of these limitations are. When we get to module 3, about 10 lectures from now, there we will actually see how to overcome these limitations using modern numerical methods, namely the finite element method, in order to analyze rigid pavements. So today's lecture is the first lecture in our series on analysis of rigid pavements using classical methods. And in today's lecture, primarily, I'm going to be deriving the main governing theory that has historically been used for rigid pavements, namely plate theory. Okay, so the lecture objectives today, we will explain the need for plate theory. We'll see why do we have to use a special theory called plate theory to analyze rigid pavements. And we will derive a particularly important and historical equation called the Sophie-Germain equation, which forms the basis for analysis of rigid pavements. So as I mentioned, module 1 was introduction, and now module 2, we've entered into classical analysis of rigid pavements. Okay, first of all, let's have a high-level view of when we talk about analyzing rigid pavements, what exactly are we looking at? So I have a picture here. Now, obviously, as the title says here, this is a JPCP pavement, jointed plain concrete pavement. It is plain because there is no steel inside the slabs, and it is jointed because there are these joints which are basically breaks or discontinuities between slabs. Each slab is characterized by a certain number of properties. So we already looked at the basic two properties, which are the elastic modulus, which is the Young's modulus, and Poisson's ratio. And that's also just about all the properties that we need in the theory. But we will require a couple of additional properties, as we'll see in subsequent lectures. First of all, we have to know the thickness of the slab. And because you have to know the thickness, obviously we also have to know the dimensions along the x-axis and the y-axis. And by x and y, I should define it. I mean, x is the longitudinal direction and y is the transverse direction. So we have to know the length and the width of the slab. We have to know the thickness of the slab. We need one more property, which is alpha. So alpha is the coefficient of thermal reaction. I'm sure all of you are familiar that it has units of per degree Celsius. So alpha is the coefficient of thermal reaction of concrete. When we consider climate-related loads or temperature-related loads, we have to consider this particular property as well. Now, in today's lecture and the next 2 or 3 lectures, we will not consider climate-related loads. But as we go further into module 2, we will also look at how climate-related loads can be accounted for in JPCP. So those are the basic properties of the slab that we have to know. There are a few other things that we also have to know. First of all, subgrade. We have to know what are the properties of the subgrade, and in relevant to the plate theory, which we'll be deriving today, we basically have to know what is the K value of the subgrade. We also have to have some understanding of any sort of connection between the slabs. So if there's any amount of load which is being transferred between the slab, that could be, for example, through a series of dowel bars. We need to understand what are the properties of the dowels, what is the geometry of the dowels. And similarly, we also have to know whether we have a shoulder and whether those shoulders are tied or untied. So naturally, we won't be able to look at all of this in one lecture. We will take about 10 lectures actually to go through all these topics. Let's go a little bit deeper into each of these components. So if you look at slabs, so first of all, in rigid pavements, slabs are of finite size. Typically, the size, which is the length and the width, is 3.5 to 4.5 meters. Note that it need not be a square. Right? You could also have a rectangular slab, although it's more common just to have a square slab, typically 3.5 by 3.5, but you could also have 4.5 by 4.5. Now, the reason I emphasize this very particularly that slabs are finite, I'm trying to juxtapose it against flexible pavements. So let's look at a flexible pavement. If you just look at it from a high level, basically for a flexible pavement, the dimensions are very long, both along the x-axis and the y-axis. The dimensions are very long. They're equal to the dimensions of the road itself. So if the road is, say, 10 kilometers long and the width is maybe 7 meters, that's 2 lanes, then basically if I look at the upper layer, the bituminous layer, that is also the dimensions of the flexible pavement, plus, of course, some thickness. So there are no discrete joints as such in flexible pavements. So that's why I emphasize this term finite size, that unlike flexible pavements, rigid pavements consists of these slabs, and these slabs are of a relatively finite size as compared to a flexible pavement. As we shall see, this is the defining characteristic of a rigid pavement, which necessitates a different theory from flexible pavements. All right, we also have a finite thickness. I think that's relatively obvious that the slab does have a certain thickness. Now, as I talked about in the previous lectures, you can have 150 mm, but that's sort of very, very low end. It's very difficult to make a slab on grade type with 150 mm. But then on the higher side, you could also go as high as, say, 400, even 500 mm is possible. And particularly if you're looking at airport runways, you can get even thicker than that. And of course, as I mentioned, we have to know the elastic properties, so E and nu, of the slab. When it comes to joints, we have to know what is the joint spacing. Now, joint spacing is equivalent to slab width. So saying that the slab has a width of 3.5 meters, is as good as saying that the joints are spaced 3.5 meters apart. So these are one and the same. We are also interested to know if there's some amount of tying or some amount of load transfer in the form of steel bars, tie bars, or dowel bars, which are provided between the joints. And if so, what are their properties? So those are some features of rigid pavements that we will consider in this module too. Now, I emphasized in the previous slide that these rigid pavement slabs, the JPCP slabs on the surface, they have a finite size, and in between them, we have these discontinuities, which we call joints. Compare that to, say, a flexible pavement where you do not have joints, and therefore you do not have discontinuities. How does that make any difference in our analysis? Now, I am assuming you've taken a course at least on UG Transportation Engineering. Perhaps you've also taken a course on analysis and design of flexible pavements. I do recommend you also take such a course. If you go back to the notes from that course, you will recall that flexible pavements are analyzed using what is called layered elastic theory. One of the assumptions of layered elastic theory is that the pavement consists of layers. Each layer is an elastic material, that is, it's characterized by the same properties, E and nu. And the last layer is semi-infinite. That's the subgrade layer, basically has a much, much larger thickness than all the other layers. It is also assumed that in the X direction and in the Y direction, the system is essentially infinite. So, of course, there's no such thing as infinite, but it's very large as relative to thicknesses. So we take mathematically that the direction along the x-axis and the direction along the y-axis is infinite. In fact, the way layered elastic analysis is done, that we generally assume axisymmetric solutions. So we actually say that the radius of the system is infinite and the depth is also infinite, but the depth consists of some discrete layers. And then using layered elastic theory, we get a very simple formulation. Well, very simple in the sense that you still need a computer to solve it, but it's a closed form solution for the evaluation of stresses and strains. Here again, in layered elastic theory, you will note that each layer is an elastic layer. That's the same assumption as in rigid pavements. However, it turns out that one major issue in analyzing rigid pavements is actually the presence of these joints. So in layered elastic theory, one of the assumptions is that the radius goes to infinity. That's in the horizontal direction. The radius goes to infinity. That is clearly not the case for a rigid pavement. For a rigid pavement, the radius is finite because the slab size is finite. We could, of course, ignore that problem. We could say, okay, I don't care about the fact that I have a joint. I'm going to assume that the slab is essentially infinite in size relative to the thickness, and then continue using layered elastic theory. You could do that. And therefore, if with that assumption that the presence of joints is not important, you could analyze rigid pavements just as you analyze flexible pavements using layered elastic theory. The problem is, as it turns out in subsequent analysis, which we'll see today, joints do actually matter. When you have a load which is placed very close to the joint, this is what we call edge loading. When we have a load which is placed close to the edge or close to the joint, it turns out that that is the location where you actually get maximum stresses developing. So naturally, if you ignore the presence of the joint, you are actually significantly underestimating the amount of stress that you have. So as it turns out, for this reason, layered elastic theory cannot really be used to accurately analyze rigid pavements, which means we have to find a different theory that in particular takes into account the presence of these joints. So what would this theory be? Historically, the theory is called plate theory, and it has been used for over 100 years to analyze rigid pavements. The main important characteristic of plate theory, which makes it useful for our analysis, is the fact that it can handle joints. In plate theory, we explicitly take into account the fact that our slab has a finite size, and so our analysis is also performed based on that finite size. The finite size, I mean in the horizontal direction. So because plate theory has this relatively simple and seemingly innocuous assumption, it makes it superior to layered elastic theory when it comes to analyzing JPCP pavements. Now, one of the additional assumptions we make for JPCP is not just that we have this slab which is governed by plate theory. So the slab is governed by plate theory, but we also assume that the subgrade is modeled as a series of infinite springs on the ground. And this sort of a model where you model the subgrade as a series of infinite springs, this is called a Winkler or a dense liquid foundation. So the plate plus the Winkler foundation together is the basic mathematical model for a JPCP pavement. So this is what our basic mathematical model will be. You will see here we do have joints, so we do have a finite size in this case. Now, you should know that there's no one plate theory. There are actually different types of plate theories. It depends on what sort of phenomenon you want to analyze. So broadly, there are three types of plate theories: thin plate theory, medium thick plate theory, and thick plate theory. So thin plate theory is sometimes also called membranes. In thin plate theory, we assume that there is no vertical deflection. So if this is our slab, we assume that the slab can expand or contract in the horizontal direction, but no displacement in the vertical direction is allowed. That's what we sometimes call a membrane. Now, I think it's very obvious that's not really accurate for rigid pavements. We know that rigid pavements, you can have some amount of displacement in the vertical direction. Indeed, we care a lot about the displacement in the vertical direction. The expansion or contraction in the horizontal direction is not that significant relative to the displacement in the vertical direction. So that brings us to the second possible plate theory, which is medium thick plate theory, sometimes also called Kirchhoff-Love plate theory. The two gentlemen, Mr. Kirchhoff and Mr. Love, they developed these theories separately, and that's why the theory is jointly named together after them. The characteristic of the Kirchhoff-Love plate theory, as we shall see in the next slide, is that we do not allow any shear stresses to develop in the cross section. We'll see the significance of that in the next slide. The third theory is called thick plate theory, also called Ulfiand-Minlin plates, and this theory does allow shear through the slab. Now, this is a particular theory. There's nothing particularly wrong with applying this theory to rigid pavements. It has been found that it's a little bit overkill. It's more complicated than using a medium thick plate theory. And it's fairly unnecessary because in general, experimentally, it has been found that rigid pavements are pretty well approximated using this medium thick plate theory. So that's why I've highlighted this in red, that among these three types of plate theories, and there are some variations within them also, among these three types of plate theories, it is the Kirchhoff-Love plates which we really use to model rigid pavements. So let's talk a little bit about this Kirchhoff-Love plate theory. So first of all, what do we have? We have a plate. Of course, and so a plate here is some kind of a rectangular object. So the geometry is rectangular. And then it has some amount of finite thickness. Now, so if we take L as the side of the slab, and if we take H as the thickness, we can take an aspect ratio L over H. If L is much greater than H, that is, if the slab is much longer than it is thick. Now, much longer is a mathematical approximation. In practice, we say if L over H is greater than 10. In that case, it has been found that Kirchhoff-Love plate theory is generally valid. So, is this applicable for rigid pavements? Well, let's consider it. We know that our size of our pavement is, say, around 3,500 to 4,500 millimeters. And the thickness may be, let's say, 200, it could be 250 millimeters. If you take the ratio of these two, you'll see that you're over 10. And even if you have a somewhat thicker pavement, you're still somewhat over 10. You might be a little bit under 10, but generally, roughly speaking, you are very close to 10 or greater than 10. So at least from this rule of thumb, L over H is greater than 10, we find that rigid pavements or JPCP slabs in general as constructed do correspond fairly well to this Kirchhoff-Love plate theory. Now, as I mentioned, in addition to the Kirchhoff-Love plate theory, for JPCP, we also assume the subgrade consists of a bed of springs, which I had previously called a Winkler foundation or a dense liquid foundation. This is a fairly easy model. All it assumes is that whenever there is some sort of displacement or deflection, and deflections we assume is only in the Z direction. So whenever there is some sort of displacement or deflection in the Z direction of the slab, then the foundation is going to apply some reaction in the opposite direction. And we assume that that reaction or stress which is developed in the foundation is directly proportional to the amount of deflection. In other words, we assume that the sigma is proportional to W, and then we have a proportionality constant, which is K. And it so happens that it is that same K, which is the coefficient of subgrade reaction. This is why we use the plate load test and coefficient of subgrade reaction to characterize subgrade, because the dense liquid foundation or the Winkler foundation uses that value as a proportionality constant between the stress and the displacement in the slab. Now, we also assume, of course, that one assumption we make, which we will relax later, is that the subgrade is allowed to have tension, which is, so if the subgrade is bending down, if the slab is bending downwards, then naturally it's pushing against the subgrade. And so you gain a reaction here of Kw. This is fine. What we also assume, if this was the neutral axis of the slab, the original neutral axis of the slab, what we assume is that when the slab is moving upwards, then the subgrade is actually pulling it back downwards with an equivalent stress, which is Kw. Now, obviously, you will realize that this is an approximation in the sense that you cannot actually have the subgrade pulling the slab back downwards. We should have what is called a tensionless subgrade or a tensionless spring. Now, that's an additional complication which we'll talk about later. We actually cannot handle that using our existing classical theories. It becomes a nonlinear problem at that point. So we will handle it using some numerical methods. But that issue aside, we have these basic set of assumptions which we make for JPCP pavements using medium thick plate theory. Okay, so let's go a little bit more into deriving the governing equation of this medium thick plate theory. And that equation then is going to be the basis of further analysis. So let's formally define what are the assumptions of this Kirchhoff-Love plate theory. There are basically 4 important assumptions, of which 2 are the most important ones. The first assumption is fairly straightforward. It's the same set of assumptions we make as in layered elastic theory, that the material, so in this case the slab, is homogeneous, isotropic, linear elastic. So homogeneous meaning that its properties are the same everywhere. Isotropic meaning the properties in any given direction are the same. So there's no directional dependence of the properties. And linear elastic meaning that it basically follows Hooke's law, that is stress is proportional to strain. What these 3 together say is that we can characterize the behavior of the material using just 2 properties, that is the elastic modulus and the Poisson's ratio. That's basically what comes out of assumption number 1. Assumption number 2 is that the mid-plane is the neutral plane and the stresses at the mid-plane under flexure are 0. Let me explain that a little more. Now, I'm assuming in this class, all of you have taken your basic classes in civil engineering. In particular, you've taken structure analysis and you know a little bit about beam analysis. We don't need a lot of the techniques there, but you do have to understand some of the basics. Now, when we have a beam, in particular, the beams that we analyze, we typically analyze what are called Euler-Bernoulli beams. I hope some of you have seen this in the past. So we analyze Euler-Bernoulli beams. What we know is that when Euler-Bernoulli beams, for example, a simply supported beam, when it is subjected to some load, it undergoes some amount of displacement. We know this. One of the basic assumptions we make is that we have some sort of a plane, and that plane, at least for plain concrete, goes exactly through through h over 2, so through the half the thickness. Our basic assumption is that at the neutral plane or the neutral axis for a beam, the stress remains 0. So if I plot the stress distribution under the load at any cross section, it will look something of this sort, where at the neutral axis, which is h over 2, my stress is going to be 0. So I'm plotting stress over here. Stress will necessarily be 0. If we have compressive stress on one side, we will have an equivalent amount of tensile stress on the other side. So if this is some sigma c, then this is going to be some sigma t. And we know that sigma c is equal to sigma t in value. The sign will be the opposite. Now, this was something that we learned for beams. And in beams, we call this particular axis or this particular depth as the neutral axis. When we come to Kirchhoff-Love plates are basically a 3-dimensional analogy of beam theory. So Euler-Bernoulli beams, where you basically have an x-axis and a y-axis, as I've drawn over here. The analogy in plates for that is Kirchhoff-Love plates. So everything you learned about beams or Euler-Bernoulli beams equally applies to Kirchhoff-Love plates. Okay, so what we call the neutral axis at mid-depth in Euler-Bernoulli beams, we simply call the neutral plane at mid-plane for Kirchhoff-Love theory, right? So the terminology is a little bit different, but the fundamental idea is the same. That is, stresses at the mid-plane or at the neutral plane are 0 under flexure. So that's an assumption that we continue to make in Kirchhoff-Love plate theory. The third assumption is relatively simple. Only transverse loads are applied. So as you know, when we analyze Euler-Bernoulli beams, whether it's a concentrated load or a UDL, all the loads are only being applied along the y direction, which we call the transverse direction. And the other direction, x direction, is called the longitudinal direction. So we only apply loads along the transverse direction. That's something we already studied in Euler-Bernoulli beams. Same logic applies in Kirchhoff plates, that all loads which are applied are only applied and acting along the transverse direction. That could also be a moment, by the way. It doesn't actually have to be load, it can be a moment. But nonetheless, it is still a moment which is causing flexure or deformation in the transverse direction. This is how we basically assume that the member is in pure flexure. The last two assumptions, which I've highlighted in bold over here, these are the most fundamental assumptions. They are assumptions of what we call a kinematic nature, and we'll see what that means in the following slides. The assumption is as follows. Planes perpendicular to the neutral plane before bending remain perpendicular after bending. Okay, so let's look again at this Euler-Bernoulli beam diagram, which I drew over here. Before bending, I had this neutral axis. And if I draw a plane over here, which is perpendicular to it, so this plane before bending is perpendicular to the neutral axis. Now, after the beam has undergone bending, what if I try to draw the location, or if I sketch out the location of this plane again, it is still going to be perpendicular to the deformed shape of the neutral axis. This is a basic assumption which we make. Planes perpendicular neutral plane, in case of plates, planes perpendicular neutral plane before bending remain perpendicular after bending. So this 90-degree angle here is going to stay a 90-degree angle after bending. It's a very, very key assumption, which will then give us a certain set of simplifications which we'll make in our analysis, which we'll see in the next slide. And then we also assume that transverse strains, also called shear strains, are not admissible. So all the strains are happening in the longitudinal direction, and the strains are giving rise to stresses. So all the strains are happening only in the longitudinal direction. In the transverse direction, which again is basically through the depth, we do not have any strains. These two are perhaps the most basic and most important assumptions. They form a set of constraints which we call kinematic constraints, and they're going to help us derive the governing equation for these Kirchhoff-Love plates or medium thick plates. Okay, so let's go into doing this derivation for these plates. So here what I have is I have a diagram of a beam. So again, the Kirchhoff-Love plates are a higher dimensional analogy of Euler-Bernoulli beams. So it is instructive to start doing this analysis on beams because the diagram and the mathematics are a little bit simpler, and then we will generalize it for plates. So let's start by looking just at an Euler-Bernoulli beam. So what I have here is I have a beam which is under some amount of loading. In this case, it's moment, so it doesn't actually matter what the loading is. And therefore, it has undergone some amount of flexure or bending, which you can see in the diagram over here. Now, I have taken out a little piece shown in red. So that's a little slice of this beam, which I've taken out. And what I have here is that originally I have the neutral axis, and I am going to define all my directions or all my depths with respect to the neutral axis pointing downwards. This is generally how we always define it. So pointing downwards, I have the depth on the neutral axis, y. Now, obviously, if I'm going in the opposite direction, that is, if I'm going above the neutral axis, then my depth is simply going to be negative. So that's what it means, that at the neutral axis, y is equal to 0. And as you go down from the neutral axis, y increases. Therefore, if you go up, y is negative. Okay, so what if I look at a tiny little strip over here, which has been highlighted in this circle, we can there highlight it over here. Now, what's happening here is what we can do is in this tiny little red strip over here, which we've highlighted, we can simply extrapolate these two planes out. They will meet at some common point. We can define the distance from this common point up to the neutral axis of this deformed beam as some sort of radius. This is called the radius of curvature. So it's some sort of radius r. Now, if we take a look at this tiny little rectangle over here, this tiny little triangle over here, what we find is, first of all, this line, or let me redraw this in this way, this particular line, this hypotenuse, this is going to be perpendicular to the neutral plane. That goes back to our assumption in the previous slide, which let me highlight that again. Planes perpendicular neutral plane before bending remain so after bending. So before bending, this particular line, which is the hypotenuse over here, was perpendicular to the neutral axis, and therefore it will continue to remain perpendicular. That's a pretty important assumption which we're going to make use of. So if we consider this little triangle over here, what we can see is that initially this little arrow here, which has been marked at epsilon. So this particular plane, which is marked here with epsilon, this is at some depth y. It can be any plane. It doesn't matter which one it is. So it's some plane which is at depth y relative to the neutral axis. And then what we see, of course, you will note here that this y is actually going above. So it's actually minus y because of our sign convention. And what we see here is that we have this little deflection over here, which I've marked as epsilon. So initially this deflection wasn't there. It is because of bending that this additional deflection has added up. And that's why we have this little amount over here, which is called epsilon. What we will see is if we use the similar triangles from here, what we basically will get is this relation which is highlighted over here, that epsilon is equal to minus y over r. And that basically comes from taking the tangent of, it basically comes from taking the tangent of theta. So if we write that tangent of theta, then that is basically equal to this little distance divided by y. But then we can also, that's this distance divided by y, but we also have theta over here, which is in the center. So this theta is going to be this overall distance divided by r. So if we take the change in distance divided by r, that gives us epsilon. And so epsilon over y is equal to minus 1 over r. And that basically gives us epsilon is equal to minus y over r. So without going into the entire detailed derivation, we get this very important relationship which relates the strain. And again, this is the longitudinal strain or the bending strain. This relates the bending strain to the at any depth to the radius of curvature for a beam. Okay, we need to do a couple of more analysis. So let's again consider that tiny little strip that we saw over there. So we have a small strip. I'm exaggerating the size over here, but we have a small strip, and this is going to be some radius r, and we have some central angle theta. So if we say the length of this strip is some s, then as all of you might know, and this is a very small strip, so this is d theta in between. We all know this relationship r d theta is equal to ds. Basically, the circumference of this little section, when we will make a quick assumption here in a second about this section, but the circumference of this little arc is basically going to be equal to the radius into the central angle if this radius is very small, if this central angle is very small. So we have r d theta is equal to ds. We can just divide both sides by x and we get this first relationship, r d theta over dx is equal to ds over dx. Okay. Now, from here, we have to do a couple of more calculations. Now, one assumption I'm going to make here, I'm going to define this term W. W is going to be my transverse displacement. So if this was my original beam and my beam has undergone some amount of bending, at any given point, I'm going to define this displacement as W. So what I have here is, if I take the tangent of theta, I can show that the tangent of theta is going to be equal to dw over dx. And you can derive it yourself. It's basically just from this triangle. It's relatively simple. But the tangent of theta is dw over dx. And now what I can do is I can take the derivative on both sides. And what I will get is that d theta over dx, which is one of the terms which we have in our original equation. So I'm just going to call this equation 1. So in equation 1, d theta over dx, we're trying to find some kind of an expression for this in terms of w. So we have one kinematic constraint, which is tangent of theta is equal to dw over dx. By the way, the only reason we are able to make this assumption is because we assume that this plane section has continued to remain plane, that there is no warping or any sort of non-linearity in this section. So this section which I've highlighted here, this is also a straight line or it's plane. Because of that assumption, we can then write out this equation over here. So tan theta is equal to dw over dx. If we take the derivative on both sides, we get d theta over dx is equal to w double prime, which is the second derivative of w, plus 1 plus w prime whole square. I hope all of you have seen this, how to take the derivative of a tangent. And well, this will basically be take the inverse derivative. So we take theta is equal to tan inverse of w prime, and then we take the derivative of tan inverse with respect to x, and we'll get this expression. So this expression is basically the derivative of the arc tangent or the inverse tangent. Okay. We can also write through this little triangle over here, we can also write that ds square is equal to dx square plus dw square. This is just Pythagoras theorem. Rearranging this slightly, so we can divide both sides by dx. Rearranging this, we will basically get ds over dx is square root of 1 plus w prime whole square, square root of 1 plus w prime square. So we now have an expression for ds over dx. We have an expression for d theta over dx. Both are in terms of w, which is the displacement, the transverse displacement. We substitute into equation 1 and we will get this term over here, that 1 over r is w double prime divided by 1 plus w prime square, the whole thing raised to the power of 1.5. Now we make a very important assumption. We assume that our displacements are small. And that's a basic assumption we make in small strain assumptions. So this assumption is called small strain assumptions. If we had larger strains, then we could not make this assumption. But if we assume that we have small strains, then we assume that w prime square, that is the square of the slope, is very, very small. The slope is small, which is what we mean by a small strain assumption. And then the square of the slope is basically infinitesimal. We can neglect it. So we take w prime square tends to 0. And then for a beam, we'll end up with this relationship. 1 over r is the second derivative of w. So the inverse of the radius of curvature is the second derivative of the displacement. This is the basic relationship between beam curvature and deflection. Now, that was for beams. As I mentioned, for slabs, the slabs basically are a two-dimensional analogy. So in beams, we had this coordinate system. We had relative to the neutral axis, this was the x-axis, and we had this as the y-axis. Now, when we come to plates, it's just a higher dimensional analogy. So in plates, this is what our plate looks like. We have now x and y are our horizontal axes, and then z, which will go into the, or actually it will come out of the plane like this, z. So z is simply going to be our third axis, which we were calling y for the beam. So we can similarly derive and write the following two equations. We now, instead of having, whenever there's some amount of bending in the plate, instead of the bending having only one radius of curvature, depending on which axis you're measuring it against, you will actually have two radii of curvature. That's Rx and Ry. So analogous to the previous slide, where for a beam we had 1 over r as the second derivative of w, what we have now is 1 over r is this 1 over Rx, that is the radius of curvature with respect to the x-axis, is the second derivative of w with respect to x. You will note here we have this del square, so this is a partial derivative. We assume here that w is a function of x comma y. Note here w is not a function of z, and that comes basically from this basic assumption that transverse strains are not admissible, which means that let me draw it this way, if transverse strains are not admissible, that means if I've got bending over here and my deflection at any point relative to the original configuration is w, then what that means is the deflection of any other point relative to its original configuration also remains w. So I do not have any displacement in the transverse direction. That's basically one of the basic assumptions that we made about plate theory. That's also an assumption made in Euler-Bernoulli theory. So that's basically another way of writing is w is a function of x and y only. It's not a function of z. So 1 over Rx is the partial derivative of w with partial derivative of x, second derivative, and similarly for 1 over Ry. We have these two relationships. Now, recall that we derived the relationship for a beam of epsilon is equal to minus y over r, where y was the distance from the neutral axis for a beam. We look at it in a different way for a plate. In a plate, x and y are our horizontal directions, and so we take z as our vertical direction. And again, the distance from the neutral plane this time, not neutral axis, but neutral plane, the distance from the neutral plane we write as z. So analogous to what we did for a beam, we can write for a plate as epsilon is equal to minus z over r. Now, of course, that depends on which direction you're doing it. So I can have epsilon x is equal to minus z over rx, and similarly epsilon y. 1 over Rx, in our previous slide, we also already showed its relationship with W. And so if we substitute that in, we will get this expression, that epsilon x is minus z del square W over del x square. Similarly, we can get a relationship for epsilon y. These two are the normal strains. And then for the shear strain, we can also get epsilon xy is minus z del square W over del xy. This you might also write as gamma xy. Regardless, it doesn't matter which strain you're using. Now, recall that one of our basic assumptions which we made was that our material basically follows Hooke's law. So it's linear elastic, homogeneous, isotropic. In that case, the relationship between stress and strain, which is basically Hooke's law, is what I've written over here, that epsilon x has some contribution from sigma x, it also has some contribution to sigma y, and that contribution depends on the Poisson ratio. Similarly for the other normal strain and the other shear strain. So now what I can do is I can rearrange this. So with these equations which I have down here, I can write epsilon x I can write sigma x in terms of epsilon x and epsilon y. Similarly sigma y, similarly tau xy or sigma xy. And then I can substitute for epsilon x, epsilon y, and epsilon xy. I can substitute them. If I do that, I basically will end up getting I will end up getting this equation, which is highlighted over here, that sigma x is minus e over 1 minus nu square z into this term over here. Similarly for sigma y and similarly for sigma xy. So again, to summarize, the way we did this was, first of all, we established the relationship 1 over r is equal to 1 over rx is equal to the second derivative of w with respect to x. Similarly for 1 over ry. We also established that whether it's for a beam or it's for a plate, epsilon is minus y or minus z over r in the case of plates. We combine these two relationships to get this relationship for epsilon x, epsilon y, and epsilon z in terms of w. We used Hooke's law in that case to convert these strains into expressions for stresses in terms of W. So finally, we have some expressions for stress in terms of W. So moving on, I'm sure all of you have studied this particular relationship, that the moment along any cross section can basically be negative integral of z into sigma dz done along the entire cross section. So that's the same relationship which we have over here, that moment along x direction is the integral minus z into epsilon x dx from minus h over 2 to plus h2. Why is it from h over 2 and not from 0 to h? Because the neutral plane is our reference point. So we assume that the neutral plane is where z is equal to 0. So that's how we go from minus h over 2, which is the top surface, to h over 2, which is the bottom surface. So this is basically our coordinate system. Similarly, we can write for mx and we can write for mxy. We already had expressions for sigma x and sigma y, and these were in terms of, this was basically some form of z into something which was a function of w. Note again that w was a function of x comma y. So w has no relationship to z, which means as far as this integral is concerned, the integral is with respect to dz, whatever terms we have which are with respect to w, they were essentially constants for the integration. The only integration that we will perform is basically with respect to z. And so this basically becomes z square over 2 from minus h over 2 to h over 2. I will let this will be z cube over 3, because sigma x, we already had a z over here. So we're going to multiply with another z. So we are taking an integral of z square. So we get z cube over 3 from minus h over 2 to h over 2. When you do that, you end up finally with these relationships, that mx, my, mz, mxy are some value d. I'll define d in a second, but it's d and some derivative of w. D, if you actually do the integration, and again, I encourage all of you to actually do this integration, don't just take these values at face value. When you do the integration, it works out to this relationship, d is equal to eh cube divided by 12 into 1 minus nu square. You will agree here, I showed you I had a z cube over 3, which will be evaluated at minus h over 2 and plus h over 2. So when you substitute that, you'll get an h cube in place of z cube, and that's why you have an h cube over here. So at least at one level, you understand that this is correct. So we get eh cube divided by 12 into 1 minus nu square. This is what we call the plate stiffness or the flexural rigidity of the plate. You have actually, all of you with a civil engineering background, you have seen this before. We actually have a similar analogy for Euler-Bernoulli beams. In Euler-Bernoulli beams, we have this term EI, which we also call the flexural rigidity or the beam stiffness. In this case, instead of EI, we have this term called D, and D in turn is the plate stiffness. So this plate stiffness D is actually a very important term. It will come back to us in a bit. We will see in a couple of later lectures. Okay, so all of this stuff which we've done is we are just relating some amount of stresses and strains. We are taking advantage of certain kinematic constraints which exist for plates. Now what we can do is ultimately we want a governing equation which is going to relate our displacements with our external load. Again, the external load is only going to be transverse, so I'm showing it with some symbol Q, which I've shown in this diagram over here. So typically what we do in these cases, and I'm sure all of you have done this at some point in your solid mechanics class, let's take a small differential element of a plate, and we will of course load it with some amount of loading which is Q. Now in this differential element, in that case, this is basically of size some dx, and some size of dy. Of course, the depth continues to be equal to z, or continues to be equal to h. So what we see here is, if we do a force balance, then on one side of the force balance, we are going to have, let's say, some moment mx. And on the other side, we will have another moment, which is m of x plus delta x. And I'm sure all of you have seen this practice, that this can be written using a Taylor series approximation, and we just truncated to the first term, that this is equal to m of x plus delta y into del mx divided by del my. Del mx, sorry. And this can be x. So I'm sure all of you have seen this particular relationship throughout. So what we do is, then on one face we have an mx, the other face we have mx plus some delta x into del mx over del my, del x. And similarly, we can do that for the shear forces also. We have no shear displacements, but we do have shear forces. So keep in mind, shear displacements and shear forces are two different things. We don't have any shear displacements, but we do have some shear forces. So as we always do in civil engineering, we calculate the equilibrium. We know that if this differential element is in equilibrium, then the sum of all forces in the z direction are going to be equal to 0. If you do that, what you will get is, so if I just draw it out here, what we have is, we might have some shear over here, which is V. Let's say this is Vx, because we're doing it in one particular direction. In the other side, we will have, in the opposite direction, we will have some Vx plus delta x del Vx over del x. So the net balance between them is del Vx del x. And similarly, in the other direction, we have del Vx del y. The sum between them, the balance between the Vx and Vy, is going to be obtained through this additional forces which we have, which are the external loading that we are applying. So we get this first equation when we take the force balance along the z-axis. Similarly, we can take a moment balance along the x and the y-axis, and we will end up getting these two particular equations. These equations are going to relate our moments with our shear forces. What we can do at this stage is, we can substitute this Vx into this first equation. We can substitute this Vy also into the first equation, and we will get this equation over here. This is an equation of equilibrium. So this is our equilibrium equation for plates. It's telling us how the moments are balancing each other so that they are in equilibrium with the external load applied, which is Q. But as we saw, we do have a relationship also between M and W. So if we substitute these relationships in, you will note here M is some second derivative of W. So second derivative of W with respect to X or Y. M is some second derivative of W. And in this relationship, which is the equilibrium relationship, we have a second derivative of N. So if we substitute those expressions here, we will get some fourth derivative of W. And that's basically this equation we get over here. This is what we call a biharmonic equation, and we can very easily write it in the short form, which is D. Again, this is the flexural stiffness. So D into del 4 W is equal to minus Q, which is the external load, where del power 4 is basically this operator, which I've highlighted in the box over here. This is the governing equation which relates our external load Q to our displacements W. And this is a very celebrated biharmonic equation. This is called the Sophie-Germain equation. Little bit of history, which I'll take a couple of seconds. So the name over here, Sophie, was actually a female scientist in France. And for a long time, because of the social era that was, she was actually not given credit for this equation. It's a later appropriate correction of history that historians have found that she also derived this equation along with Mr. Germain over here, who was a male scientist. And that's why for some time this was just called the Germain equation. But now correctly we give credit to both scientists who derived this, and we call this the Sophie-Germain equation. This is almost the basic equation that we use for rigid pavements, with one exception. That is, if I go back here, I also have a bed of springs. That's one thing which I did not include so far in it, that we also have a bed of springs which provides a Winkler foundation. However, this is very easy to do because the force applied by this bed of springs for this differential element is basically going to be equal to Kw. So if W is the displacement, the stress is Kw, and then this is simply equal to dx dy, which is the size of the differential element. So I can actually just plug it into this balance equation, and I'll simply get a slightly extra term over here, which is Kw. And so adding that, I get the following equation. D into del power 4 W plus Kw is equal to minus Q. This equation is a combination of This first term here, this is the Sophie-Germain equation. It talks about how the displacement in a medium thick plate is related to an external load. Obviously, it requires certain boundary conditions also. When we add Kw over here, we are essentially adding back those boundary conditions which we require. The boundary condition being that we have this Winkler foundation or a dense liquid foundation. So this one equation over here is telling us that if we have what I previously called a slab on grade, that if we have a plate, a slab, which is sitting on the subgrade, the plate is modeled using Kirchhoff-Love theory or medium thick plate theory, which means the plate is modeled using the Sophie-Germain equation. And then we have the Winkler foundation, which is just providing some additional force, which provides a force balance. Then we get this equation, which I've highlighted in the box over here. This forms the basic equation of jointed plane concrete pavements, which is what we use further to analyze. One thing you may note, which we'll also come back to in subsequent lectures, is this is a differential equation. When we are solving differential equations, we typically also require boundary conditions, at least when we're solving boundary value problems. We also require boundary conditions. Now, the reason we require boundary conditions is we basically need to make sure that we have a unique solution. So what would happen is if I did not have this Winkler foundation, and if I loaded my plate, then my plate would just fall through the ground basically. There's nothing to prevent it from falling. In other words, there's nothing to prevent it from having rigid body motion. So the purpose of providing any boundary conditions is to prevent rigid body motion from happening. But as we see, if I have this slab which is on this Winkler foundation, then when I load this Winkler foundation will prevent it from simply falling through the ground because you're going to have a reaction coming from the subgrade. And so the presence of the Winkler foundation by itself is sufficient for this system to have a unique solution, and therefore we do not require any additional boundary conditions or any special additional boundary conditions which have to be applied in terms of constraining displacements. This equation by itself can be solved, assuming of course that we have a couple of free sides, etc. But this equation itself can be solved, but it's not that easy to solve. First of all, it's a biharmonic equation. I would bet that most of you have not actually solved biharmonic equations in the past. So this might be the first time you're even looking at such an equation. And deriving the solution for such an equation is also not an easy matter. Fortunately, there are many before us who've taken the trouble of actually trying to solve this equation, and we do have some very good solution for these plate theory equations for JPCP. The most celebrated of these were the solutions provided by H.M. Westergaard, Harold M. Westergaard. And in the next lecture, which is lecture 6, now that we have established this basic governing equations for JPCP pavements, in the next equation, we are going to look at the first and most celebrated set of analytical solutions which were derived over 100 years ago for this equation, which were Westergaard solutions. So I will see you in the next solution where we will look at particular solutions to this differential equation, and from there we will see certain behavior in terms of stresses when rigid pavements are loaded. Thank you.